The following program is brought to you by Copeland Corporation.
Hi, my name is Glenn Hannigan. I'd like to help you understand some of the common causes of compressor failures. When looking into this subject, you have to start with one very interesting fact. Industry records clearly show that replacement compressors, whether they are new or remanufactured, fail at a rate many times greater than compressors going into new systems. This clearly demonstrates that there is often a problem with the system itself. This problem has caused the original compressor to fail and will probably cause the replacement to fail as well. So how do you tell if your failure was caused by a system problem? The answer is inside the failed compressor. You have to open up the compressor and look for the various clues that can show you the true problem. Many failures end with the motor burnout, misleading some technicians into thinking that the root problem was electrical. This just isn't the case. Inspections show that the problem usually starts somewhere else and gets steadily worse until it causes the motor to fail. The blame goes to the motor. The true problem remains. There are 5 main causes of compressor failure: fluttered starts, refrigerant floodback, slugging, overheating, and loss of oil. We're going to look at fluttered starts in this tape and learn what fluttered starts are, what causes them, and what we can do to prevent this problem. Let's watch.
This diagram represents a basic refrigerant-cooled compressor. When a compressor starts, the suction pressure is lowered and refrigerant vapor flows to the cylinders. Oil is pumped to the bearing surfaces, providing proper lubrication. Whenever a compressor is started with enough liquid refrigerant in the crankcase to dilute the oil and overcome the oil's ability to lubricate properly, a condition known as flooded start exists. This refrigerant gets into the oil during the off cycle through a process called migration. Migration is a natural result of the difference in vapor pressure between the refrigerant and oil and occurs anytime refrigerant and oil are in contact with each other and the compressor is not operating. During the off cycle, some migration always occurs, and if the amount of refrigerant that is migrated is small, this will not be a problem. But if the oil temperature in the crankcase is too low compared to the evaporator temperature, the off cycle is too long, or if there is an excessive charge of refrigerant in the system, migration can become a real problem. It is important to realize that only refrigerant vapor migrates, not the actual liquid itself. When a compressor is off, the refrigerant vapor is drawn to the oil because oil has a lower vapor pressure than the refrigerant vapor. The cooler the oil, the lower its vapor pressure, and the greater the attraction for refrigerant vapor. During the off cycle, the refrigerant vapor in the crankcase begins to condense in the oil and dilutes it. At the same time, the liquid refrigerant continues to vaporize in the evaporator and travels through the suction line to the compressor. This vapor condenses in the oil and the process repeats. This will continue as long as there is liquid refrigerant in the evaporator. Since the refrigerant-rich oil is more dense than pure oil, it will settle to the bottom of the crankcase, leaving purer oil on top to absorb more refrigerant. If there is more refrigerant than the oil can hold, the excess refrigerant will settle to the bottom of the crankcase. A migration problem can easily be confused with high oil level, since they appear identical when looking into the sight glass. But when a refrigerant-cooled compressor starts up with this refrigerant-rich oil in the crankcase, the sudden reduction in pressure causes a violent reaction. The lower pressure causes the refrigerant in the crankcase and motor compartment to literally explode out of the oil. This explosion looks like a white foam. It is actually liquid refrigerant and oil droplets. The explosion can last for minutes or just a few seconds at each startup, depending on how much refrigerant is in the oil. If you are watching at the time of startup, you will see this foam in the compressor sight glass. The damage occurs when the refrigerant foam washes the oil from the bearings, crankshaft, and connecting rods. The amount of refrigerant in the oil and which rods are closest to the mixture when it explodes will determine how much damage is done. The damage shows up as erratic wear or scoring patterns in the lower connecting rod and crankshaft bearing surfaces. This wear opens up the bearing clearances and causes lower net oil pressure over a period of time. With flooded start damage, you frequently find one rod and crankshaft throw scored or seized, with the other bearing surfaces on either side in good condition. If the rod actually seized, you may even find it broken. The explosion can even be large enough to force the mixture through the crankcase ventilating passages or out of the motor compartment, following the vapor passages into the cylinders, leading to a condition known as slugging. With an air-cooled compressor like this one, the crankcase pressure reduction is much slower, and the explosion of the refrigerant-rich mixture will not occur. But the dilution of the oil by refrigerant will still wash lower bearing surfaces in an erratic pattern, causing scoring, breakage, and wear. Let's look at some of the factors that affect migration. First, how long is the compressor off? The longer it is off, the more time is available for migration to take place. Compressors that run continuously or are not off long enough for the oil to become too cool generally do not have migration problems. Secondly, what is the coldest ambient temperature the compressor is exposed to? Even though crankcase heaters are commonly used to raise oil temperature and reduce migration in ambience below 50 degrees Fahrenheit, they may not provide sufficient heat. Is there a large temperature difference between the saturated refrigerant in the evaporator and the oil in the compressor? For example, if a central heating and air conditioning system has been in the heating cycle, or a commercial refrigeration system has been in electric defrost, the compressor may be cool in relation to the evaporator, and dangerous quantities of liquid refrigerant may migrate to the compressor before startup. And finally, is there more refrigerant charge in the system than the oil can safely absorb during the off cycle? Compressors have a recommended maximum system charge limitation. If the limit is exceeded, the compressor may need crankcase heaters or continuous pump-down systems added. If any situation makes excessive migration possible, and you suspect that crankcase heaters may not be effective, the positive way to prevent migration is to apply a continuous pump-down cycle. The continuous pump-down cycle has a solenoid valve in the liquid line operated by the temperature control. This allows the low side of the system to be evacuated at the end of each running cycle. The compressor is cycled off by a low pressure control. But beware, if anything interrupts the pump down before the low side is pumped free of all liquid, or if any refrigerant leaks from the high side to the low side, migration can still occur. Proper low pressure control settings must be used, and one-time pump downs should be avoided. Let's summarize. To ensure that flooded starts are not a problem, the service technician should 1. Locate the compressor in a controlled ambient above 50 degrees Fahrenheit if possible. 2. Do not exceed the recommended maximum refrigerant charge and maintain an adequate oil level. 3. Use a crankcase heater. 4. If you feel conditions make it necessary, install and use a continuous pump-down cycle. And finally, study your entire system during the off cycle. Determine if it is a candidate for a flooded start problem. Alter your system accordingly. Flooded start problems can be avoided.
As we have seen, flooded starts can cause quite a problem. They are usually seen as uneven wear in failed compressors. Flooded starts can be difficult to detect or identify. Broken rods resulting from flooded starts may mistakenly be identified as a floodback or a loss of oil problem. Failure to develop a proper net oil pressure is often mistakenly identified as normal compressor wear, a failed oil pump, or a bad oil safety control. Since migration occurs during the off cycle, there are no pressures or temperatures to aid in the diagnosis. If the technician is not present at the time of a flooded start to witness the foam in the sight glass, there is no way to tell that a flooded start problem exists. Always remember to study your system and look for the pattern of off cycles and temperatures that might lead to a flooded start. Locate your compressor in a controlled ambient temperature whenever possible, and add a crankcase heater or a continuous pump down system if necessary. Do not exceed the maximum refrigerant charge and maintain an adequate amount of oil in the crankcase. Remember, replacing a failed compressor in a system with a problem will often gain you nothing more than another failed compressor. Study your entire system rather than looking at the individual components. Improper diagnosis and improper corrections will create a whole new set of problems. Proper diagnosis and proper corrections will make a world of difference. On behalf of all the people at Copeland Corporation, I thank you for your attention. For additional information on other causes of compressor failures, ask to see the other Copeland tapes in this series.